Welcome back to the deep dive. Today, we've got this huge stack of research. It's basically a full guide, and we're going to crack open the engine that powers, well, billions of devices globally. We're really dissecting the architecture, the history, and sort of the development DNA of Apple's operating system for iPhone, iPad, and iPod Touch iOS.
Yeah, and this is it's a crucial dive, I think. Understanding iOS isn't just about, liking the interface. It's really about getting a handle on one of the two dominant mobile platforms that today pretty much shape global tech standards, security approaches, and how software gets made.
Right.
These sources we have give us a really detailed look inside what people often call the walled garden.
So our mission today is basically to give you the shortcut to really understanding how this platform works inside. We're going to trace its pretty amazing evolution starting way back in 2007. Then I'll do a strategic comparison with its main competitor, Android.
Always important.
Yeah, and then zoom right in on the nitty-gritty mechanics of how apps are actually built and how they manage resources on your device.
It's quite a journey spanning, almost 2 decades now?
Yeah.
Leading us from, the basic functions of the very first phone OS right up to the cutting edge of on-device AI. The sources are deep, so yeah, we're planning to explore every layer.
Okay, let's unpack this. All right, so the story really kicks off with that iconic moment in 2007. Steve Jobs unveils the first iPhone, and the operating system back then, it wasn't even called iOS yet, right? It was just iPhone OS.
That's right, iPhone OS. And it was revolutionary hardware for sure, but we often forget how basic the initial software, iPhone OS 1, actually was. It had the core built-in apps, phone, mail, Safari, iPod, but, and this is key, there was no way for outside developers to build apps for it.
Ah, right. No app store yet.
Exactly. It was a closed system, really built for utility, not, extensibility.
Okay, so the real foundational shift, the thing that arguably created the whole modern smartphone ecosystem that came just a year later. iPhone OS 2 in 2008.
That was it, the debut of the App Store.
Game changer.
Absolutely. That one feature totally redefined the platform. Suddenly, the iPhone wasn't just this cool communication device. It became a customizable, sort of open-ended platform for third-party innovation. It basically created a brand new economy, a whole new type of software developer, almost overnight.
Yeah.
The App Store wasn't just a feature. It was like a whole new business model. Fundamentally changed everything.
So looking at those early years, iPhone OS 3 in 2009 brought things we take for granted now, like copy-paste and MMS.
Yeah, basic stuff now, but missing then. And then 2010 was big. The platform got its current name, iOS.
Ah, with OS 4.
Right, coinciding with OS 4. And that version brought 2 massive advances.
Yeah.
Multitasking, letting apps run in the background, even if it was a bit limited at first.
Right, like for music or calls.
Exactly. And FaceTime, which kicked off the whole integrated video calling era for Apple.
Oh.
Renaming it to iOS also kind of signaled it wasn't just for the phone anymore. It was getting ready for the iPad.
Okay, so moving into that sort of mid-era, the updates seem more focused on refining things and maybe pulling users deeper into the Apple ecosystem.
Very much so. iOS 5 in 2011 was huge for integrated services. It launched iMessage that unified messaging across devices, introduced the modern notification center, which was a big improvement, and iCloud was born, tying all your user data to Apple servers for backup and syncing.
But the next really huge change, that wasn't functional, it was visual, wasn't it? iOS 7 in 2013. That felt like a massive shift.
It was. The sources call it a visual earthquake, and that's not really an exaggeration. This is the big UI redesign under Jony Ive, moving completely away from skeuomorphism, where digital things try to look like real-world objects.
Yeah, like the fake letter calendar or the green felt in the game center. Why did they feel that shift was so necessary?
It seemed, honestly, a bit jarring at the time. Well, it was a really strong strategic move, signaling the future of digital design as Apple saw it. Skeuomorphism started to feel, dated and maybe a bit limiting. Ive's philosophy was more about digital interfaces embracing their digital nature. Flat design, bright colors, thinner fonts, modern, scalable, simpler.
Right.
It also brought in the control center, super useful, and AirDrop for that seamless local file sharing.
Okay, so the innovation keeps rolling, focusing on performance and adding capabilities. iOS 9 in 2015, that was about performance and battery life, right?
Right.
Responding to complaints.
Yeah, big focus on stability and optimizations there. Plus, they added things like proactive suggestions, and HealthKit got more robust.
And then iOS 11 in 2017, that sounds like it was really crucial for the iPad.
Definitely. It brought key features like proper drag and drop between apps, much better multitasking with the dock, and the Files app.
Finally, giving the iPad real file management.
Exactly.
Yeah.
That really started moving the iPad towards being a potential laptop replacement for some people, not just a bigger iPhone.
So if those middle years were refinement and ecosystem building, the modern era, maybe starting around iOS 13 in 2019, feels more defined by privacy and personalization.
I'd agree with that. iOS 13 brought dark mode, huge aesthetic, and potential battery win on OLED screens, and sign in with Apple.
That felt like a big privacy statement.
It was a massive strategic push.
Yeah.
Apple positioning itself as the sort of privacy-first identity provider instead of having users rely on Facebook or Google logins, directly playing into their privacy narrative.
And iOS 15 in 2021 continued that.
Yeah, focusing on managing distractions with focus mode, deeper collaboration with SharePlay, and redesigned notifications.
And the latest one covered in the sources, iOS 17 from 2023, added more social stuff. Contact posters, name drop.
Right, making the phone feel more integrated into your social interactions. Interactive widgets, too, making the home screen more functional.
Okay, here's where it gets really interesting. We need to talk about the future based on this material. iOS 18 is coming in 2024, expected to be heavy on AI features, Apple Intelligence, they're calling it apparently, plus more customization, tighter Mac integration.
That's the sort of expected evolutionary path. But the sources point to something, well, pretty dramatic. The iOS 26 shock.
Okay.
Apparently, Apple's planning to skip versions 19 right through 25. Just jump straight from 18 to 26 for the 2025 release cycle.
Whoa, skipping 8 version numbers, that's not just marketing, is it? That signals something big.
It's unprecedented for them. It implies Apple sees this next wave of features as a fundamental break from the past. Kind of like Microsoft jumping from 8 to 10.
So declaring a new era.
Exactly. The version number itself is a statement that the underlying tech and capabilities are shifting significantly.
And what defines this iOS 26 leap, according to the sources?
Okay, first, a massive visual overhaul. Something called the new liquid glass UI design.
Liquid glass. Sounds smooth, transparent, maybe.
Yeah, it suggests a really dynamic, maybe more immersive aesthetic, moving beyond the flat design of iOS 7. But more critically, the focus is squarely on advanced AI. Smarter Siri, powered by actual on-device intelligence. Live translations happening locally on the phone. Enhanced call screening to automatically block spam and scams.
On-device intelligence. That's huge for privacy, isn't it? Addressing that worry about data going to the cloud constantly.
Precisely. It lets Apple deliver powerful AI features while sticking to its security guns. Keep the processing local, minimize the privacy risk. The sources also mention iOS 26 bringing wireless charging improvements and expanding live activities into CarPlay. So continued integration.
But that jump, 18 to 26, they're really signaling this isn't just an update, it's a whole new architectural phase.
Driven by privacy-focused AI and a major UI shift. That seems to be the message.
Okay, that history gives us great context.
Yeah.
But to really get the iOS architecture, we have to compare it against, well, its lifelong rival, Android.
Right. And people often talk preferences. But the sources really lay out the deep foundational differences in how they're built, which affects everything.
So what's the absolute core difference?
It really boils down to ecosystem and hardware control. Apple runs a tightly integrated closed system. They make the iPhone, the iPad, and they make the software, iOS.
And the benefit of keeping it all in-house is?
Consistency. Yeah. Extreme consistency. It allows for really smooth performance, tight optimization, and this is huge for users' very long-term software updates. Developers also benefit because they only have a handful of hardware targets to worry about each year.
Right.
Simpler testing, more stability.
Okay, and Android is basically the opposite model.
Completely. Google develops the Android OS, makes it open source, but the actual phones and tablets are made by dozens of different companies. Samsung, Xiaomi, OnePlus, you name it.
Which leads to?
Fragmentation. That's the keyword. Performance, features, the user experience, it all varies wildly because the hardware is different and manufacturers slap their own custom interfaces, their skins on top.
Right. And that control difference directly impacts the app stores and review process too, doesn't it?
Absolutely. For iOS, it's pretty much just the Apple App Store, unless you jailbreak, which most users don't. And Apple has strict review guidelines.
Which developers sometimes complain about?
They do, because it can slow things down. But Apple's argument is that this rigorous process ensures app quality keeps the look and feel consistent following their human interface guidelines, and provides a baseline level of security.
So that friction for developers is meant to be a safety net for users.
That's the trade-off, yeah.
Yeah.
Android, on the other hand, is much more flexible. You've got the Google Play Store, but also third-party stores. You can sideload apps.
More freedom for developers.
Definitely. Faster to get apps out, more options.
Yeah.
But the sources are clear. This openness inherently means a higher risk of malware finding its way onto users' devices, especially if they download from outside Google Play.
Okay, let's talk updates, support, and consistency. This seems like a huge win for Apple's model.
It really is. From a consumer perspective, iOS devices are known for getting updates for a long time, typically 5 or 6 years of regular synchronized software updates. Your older iPhone often gets the latest iOS version the same day the brand new ones do. That keeps the device useful and secure for longer.
Whereas the Android situation is, well, messy.
It's often cited as Android's biggest weakness, yeah. Updates depend entirely on the manufacturer. Google's own Pixel phones get them fast, sure. But for most other brands, you might get 2, maybe 3 years of major OS updates and then you're done. This creates a massive number of devices running older, potentially vulnerable software. It's a significant security issue for the whole ecosystem.
And that consistency Apple pushes for extends right into the app design itself, through the human interface guidelines, the HIG.
Right. The sources emphasize how strictly Apple enforces the HIG. Apps are expected to use standard controls, follow specific navigation patterns, look and feel a certain way.
Ensures everything feels familiar.
Exactly. It creates a consistent, predictable experience across almost all iOS apps. You generally know how things will work.
Android has material design, but manufacturers seem to ignore it or heavily modify it a lot of the time.
They do. Material design provides guidelines, but manufacturers like Samsung with their One UI or Xiaomi with MIUI, they customize the look and feel heavily for branding. Which is fine, but it means jumping between a Samsung phone and, say, a Pixel can feel quite different, less consistent overall.
Let's zoom in on security and customization, often seen as being at opposite ends, right?
Generally, yeah. And iOS clearly prioritizes security and privacy in its architecture. The sources highlight several layers. The strict sandboxing of apps.
We should probably explain sandboxing quickly. What does that actually mean?
Good point. Sandboxing basically means every app runs in its own isolated container, its own sandbox. It can't easily access data from other apps or mess with critical system files without explicit permission from the user or the OS.
So if one app is malicious, the damage is contained.
Largely, yes. It drastically limits what a bad app can do. It's a fundamental part of iOS security. Then you have the controlled app store review, we mentioned, on-device processing for things like AI features.
And app tracking transparency, ATT. That felt huge when it landed in iOS 14.5.
Oh, it was massive, strategically and economically. ATT forces apps to ask your permission before they track your activity across other companies' apps and websites.
Which sounds simple, but really shook things up.
Absolutely. Architecturally, it forced developers to rethink how they handle user data and advertising identifiers. Strategically, it cemented Apple's image as the privacy champion.
And the economic impact on companies relying on targeted ads was significant, wasn't it?
Huge. The sources suggest it was intentionally disruptive. It fundamentally challenged the existing mobile advertising model that relied heavily on cross-app tracking, made targeted ads much harder and more expensive overnight. It was Apple using its platform control to really assert its stance on privacy in the market.
Okay, so strong security focus on the iOS side. Android, while improving, is inherently riskier due to its openness.
That's the general consensus, yes. Android has things like Play Protect and sandboxing too. But the flexibility allowing app installs from anywhere, deeper system access, means the potential attack surface is just larger.
And that openness leads directly to Android's strength, customization.
Exactly. If you want deep control over how your phone looks and feels, Android is the place to be. You can change the launcher, icons, themes, add widgets anywhere. You can even root the device for deep system modifications. iOS is much more locked down in comparison. Widgets exist now, sure, but system-wide customization is very limited.
So different philosophies, different trade-offs. And finally, how does this play out in the market and target audience?
Well, iOS, with its premium pricing and focus on integration and consistency, tends to be strongest in developed markets like the US, Europe, Japan. It targets users who value that smooth experience, security, and are often willing to pay a premium for it.
And Android gets the rest.
Pretty much captures the volume globally. Android dominates worldwide market share, especially in developing countries. Why? Because That fragmented hardware model means there's a huge range of Android phones at basically every price point imaginable. Accessibility is its strength.
Okay, that comparison really highlights Apple's core philosophy. Tight control equals optimization and security. So now let's get into the how. How does Apple actually enforce that control, especially regarding performance and battery life?
Right. This is where we get into the technical weeds with the application and UI view controller life cycles. These are basically sets of rules that dictate how an app and the screens within it behave, especially when they're not actively being used.
To manage memory and battery, essentially.
Exactly. If Apple wants smooth performance and long battery life, they have to strictly control what apps are doing in the background. The application lifecycle is key here. When you open, use, and close an app, it moves through 5 distinct states managed by the system.
Okay, let's walk through those 5 states. Start simple.
We start with not running. Pretty self-explanatory. The app hasn't been launched yet, or it's fully closed down, maybe forced quit by the user, or terminated by the system to free up memory. Needs a full fresh start.
Got it. Next state.
Inactive. This is usually a very brief, temporary state. The app is technically running in the foreground, but it's paused from receiving any user input or events.
Like when a phone call comes in.
Exactly. Or if you pull down the notification center over the app. It's a momentary interruption before it usually goes back to being active.
Okay. So the main state where the action happens is active.
Right. Active means the app is front and center, running, receiving your taps and swipes, doing its thing. This is where almost all user interaction occurs.
Then I hit the home button or swipe up. What happens?
The app transitions quickly to the background state. It's no longer visible on screen, but it's still allowed to execute code for a very short time, maybe a few seconds.
Just long enough to
finish up critical tasks, like saving the current state, finishing a quick file upload or download. Then the system automatically moves it to the next state.
Which is suspended. What does suspended actually mean here? Is it still running?
Not really running. When an app is suspended, it's still loaded in the phone's RAM, its memory. But the system completely halts its CPU execution. It's basically frozen in time.
So it's not using any processor power, not draining the battery.
Correct. 0 CPU time. It's kept in memory so that if you quickly switch back to it, it can snap right back to the active state instantly without reloading everything from scratch.
But it's vulnerable in this state.
It is. If the system starts running low on memory, maybe you open a big game, suspended apps are the first ones the system will quietly terminate, just purge from RAM without warning to free up resources. Then they go back to not running.
Okay, so these state changes are critical moments, and developers have to hook into these transitions using specific methods, these callbacks in the app delegate.
That's the mechanism. The app delegate is like the app's main coordinator. When the app first launches, application.didFinishLaunchingWithOptions gets called. That's the spot for initial setup databases, network configs, anything global.
And when the user leaves the app, sending it to the background,
the system calls application.didEnterBackground. This is the developer's crucial chance to save user data, pause timers, make sure any background tasks are properly initiated before the app might get suspended.
And coming back.
Application did become active. Gets called when the app comes back to the foreground, fully interactive. Developers use this to refresh data shown on screen, restart animations, maybe check if the user session needs refreshing.
Is there a last chance saloon before the system kills the app?
There is. Application will terminate. Now, in modern iOS, apps are often just silently purged from the suspended state. But if the system explicitly decides to terminate a running app, which is rarer now, this method gives one final opportunity for cleanup or saving critical data. Understanding and correctly implementing these callbacks is absolutely fundamental to building a well-behaved iOS app that doesn't hog resources or drain the battery.
Okay. That makes sense for the app as a whole. Now let's drill down. You mentioned the UI view controller lifecycle, so each screen in an app has its own lifecycle too.
Exactly. Most apps are made of multiple screens, right? Each main screen or view is typically managed by a UI view controller. And yes, each controller has its own lifecycle, managing its view's creation, appearance, and destruction.
All right, let's trace that. How does a screen get created?
It starts with initialization methods like init, coder.or, init, nibname.bundle. This just creates the controller object itself in memory. Then comes load view. This is where the controller's main view, the visual part, gets loaded, usually from a design file like a storyboard or a XIB. Or if a developer is building the UI entirely in code, they override load view to create the views programmatically.
Okay, and then comes the one everyone talks about, View did load.
Ah, yes, view did load. Probably the most well-known method in iOS development. It gets called exactly once per controller instance, right after its view hierarchy has been loaded into memory.
So perfect for setup that only needs to happen once.
Precisely. Setting up static UI elements, adding constraints,
Yeah.
making that initial network call to fetch data for the screen view did load is the place.
But the user can't see the screen yet, even after view did load.
Correct. The view is loaded, it's ready, but it's not necessarily visible. The next two methods handle the appearance phase. First is view will appear,
Called just before it appears.
right before it slides or fades onto the screen. And crucially, this gets called every time the view is about to appear, not just the first time. So it's great for things that need updating each time, like refreshing data that might have changed, or starting analytics tracking for that screen.
And then viewed appear confirms it's fully visible.
Yep. Once view did appear is called, the screen is fully on display, animations are complete. This is the time to kick off things that require visibility, like starting a video playing, or maybe intensive animations.
Okay, makes sense. And when the user navigates away.
The disappearance sequence starts. View will disappear is called just before the screen starts animating off. Good time to save any temporary state, dismiss the keyboard, stop animations related to that screen.
And after it's gone.
View to disappear is called once the view is completely off screen, used for final cleanup tasks related to that view's presentation.
And the very end of the line for a screen controller.
That's DNIT. This method is called when the system determines the view controller object is no longer needed at all. Like if you navigated back from it and it's not expected to be shown again soon, it gets deallocated from memory, releasing all its resources. That completes the life cycle.
Okay, so we've talked about control and life cycles. Another key part of how Apple enforces that consistency we discussed is by providing this standard set of pre-built UI pieces, right? The developer's toolbox using UIKit components.
Exactly. Apple provides and strongly encourages developers to use these ready-made building blocks, things like standard buttons, lists, text fields. Using them ensures apps generally follow the human interface guidelines, look familiar to users, and behave predictably.
Saves developers reinventing the wheel every time.
Right, and it helps maintain that consistent iOS feel. Let's run through some of the most common ones mentioned in the sources.
Okay, starting with basic communication. Labels, buttons, text input.
Sure, UI label is fundamental, just displays read-only text. Titles, descriptions, status messages, process, whatever. UI button is your standard tappable button for actions or navigation. Then UI text field for single-line text input. Think login fields, search bars.
And if you need more text, like for a comment box.
That's where UI text view comes in. It handles multi-line editable text. And for showing pictures, obviously you used UI image view.
All right, let's get to the really core components for displaying data. UI table view and UI collection view. These seem to be everywhere in iOS apps.
They absolutely are foundational. UI-table view is for displaying scrollable lists of data in single-column rows. Perfect for contact lists, setting screens, email inboxes, feeds. UI collection view is more flexible. It lets you create grid layouts, horizontally scrolling lists, staggered grids, really complex custom layouts. Think photo galleries, product grids, and shopping apps, that kind of thing.
But the key insight here, according to the sources, is how they handle potentially huge amounts of data without killing the phone's performance. That's cell reuse, right?
Yes. Cell reuse is the magic behind smooth scrolling in iOS. It's absolutely critical. When you scroll through, say, a list with thousands of items, the system doesn't actually create thousands of little view objects in memory. That would crash the phone instantly.
So what does it do instead?
It creates just enough cell objects, maybe 15 or 20, whatever fits on the screen, plus a couple extra. As a cell scrolls off the top of the screen, the system doesn't destroy it. It puts it in a reuse queue.
Okay.
Then, when a new row needs to appear at the bottom, the system pulls one of those recycled cells from the queue, quickly updates its content with the new data for that row, and puts it on screen.
So it's like constantly recycling a small number of containers, just changing what's inside them as you scroll?
Perfect way to put it. It's incredibly efficient on memory and CPU. That's why iOS lists generally feel so smooth, even with tons of data. It's an architectural optimization built right into UI-table view and UI collection view.
Clever. Okay, what about other standard controls? Switches, sliders.
Yep, common utility controls. UI switch for a simple on-off toggle. UIS slider for selecting a value along a range, like screen brightness or volume. UI progress view shows, well, progress, like for a download or upload bar. Using these standard ones means users instantly know how to interact with them.
And finally, some system-level UI things, like alerts.
Right. UI Activity Indicator View is that little spinning wheel, the spinner, that tells the user, hang on, I'm working. Keeps them informed. And UI Alert Controller is really important. It's the standard way to show pop-up alerts, warnings, or sheets of options, action sheets. Because it's a system component, critical messages like permission requests or error dialogues always look and behave the same way, which builds user trust and reinforces those HIG.
Got it. So using these tools helps create that consistent iOS experience. Now, shifting slightly to how apps are released, let's talk about versioning. The sources mention 2 different version numbers.
Yeah, this often confuses people, but it's crucial for developers and the App Store process. iOS apps have 2 main version identifiers. The one users see is the marketing version.
And that's set using CF bundle short version string.
Correct. Its format is usually the familiar major.minor.patch style, like 1.2.3 or 2.0. You see this number in the App Store listing, maybe in the Apps About screen.
Its job is purely communication.
Purely external communication.
Yeah.
Tells users what version they have, signals how big the update is, major new features 2.0, minor tweaks 1.3, bug fixes 1.2.1.
Okay, so what's the other version number, the build number?
Right, that's CF bundle version. This one is mostly for internal use for developers, testers, build systems, and the App Store itself.
And its format is different.
It could be just a simple incrementing number, like 101 or 102, 103, or sometimes it mirrors the marketing version with an extra build identifier, like 1.2.3.45.
What's its main purpose then, if users don't usually see it?
Tracking specific builds. Every single time a developer uploads a new build of their app to App Store Connect, even if the marketing version, like 1.2, stays the same between uploads, the build number must be unique and higher than the previous one for that version.
So the App Store uses it to distinguish between different test versions or minor iterations of the same marketing release.
Exactly. It ensures traceability. You know precisely which compiled binary corresponds to build 105 versus build 106, even if they're both marketed as version 1.2, prevents a lot of confusion during testing and release.
All right, the last major architectural piece we need to dig into is the programming language itself. For years, iOS development meant Objective-C, but now the standard is Swift. This wasn't just changing syntax, was it? It sounds like a fundamental architectural shift.
Oh, absolutely. It was a huge strategic move by Apple. They needed a language for the next few decades of development, one that prioritized safety, speed, and modern programming concepts. Objective-C was powerful, and it served its purpose, but it had limitations, especially around safety and complexity.
Okay, the sources break down key differences. Let's start with just the look and feel, syntax and readability.
Right. Objective-C is, well, let's say it's distinct. Very verbose, lots of square brackets for method calls, long descriptive method names. It could be quite dense to read.
And Swift.
Swift aimed for clean and modern. The syntax is much closer to languages like Python or JavaScript. Fewer semicolons needed, less boilerplate code. It's generally considered much more readable and expressive, easier to learn for newcomers too.
Okay, maybe the biggest practical difference for developers. Memory management.
Yeah.
Objective-C was notorious for this, right?
Infamous, perhaps. Before Apple introduced automatic reference counting, ARC, memory management in Objective-C was manual. Developers had to meticulously track object ownership using retain, release, auto-release.
Sounds error-prone.
Extremely. It was incredibly easy to make mistakes, either leaking memory by forgetting to release objects or crashing the app by releasing something too early, a dangling pointer. Debugging these issues was a nightmare.
ARC helped in Objective-C, but Swift took it further.
Yeah, ARC was bolted onto Objective-C later. Swift was designed with ARC built in from the ground up. It handles most memory management automatically and elegantly. Plus, Swift introduced concepts like weak and unowned references to make it easier to break potential retain cycles situations where objects hold onto each other and never get deallocated. This made memory management much safer and less of a constant worry for developers.
That focus on safety seems core to Swift, which brings us to type safety and optionals. How does Swift prevent errors that Objective-C might have missed?
Objective-C is more dynamically typed. That means you could sometimes send messages, call methods, on objects that didn't actually respond to them or have type mismatches that would only cause a crash at runtime when the user is actually using the app. Swift is strongly typed. The compiler checks types rigorously before the app even runs. This catches a huge category of bugs during development.
And optionals. They seem like a really core Swift concept. Can you explain them simply?
Okay, think of an optional variable marked with a variable as a box. That box might contain a value like a number or some text, or it might be empty. Nil. Swift's compiler forces you to safely check if the box has something in it before you try to use the value inside. This is called unwrapping. You can't just assume the value is there.
Why is that so important?
Because trying to use a nil value, accessing a property on it, calling a method, is probably the single most common cause of crashes in many programming languages. Optionals make handling the possibility of absence explicit and safe, preventing countless runtime crashes.
Makes sense. How about error handling? How did Swift improve on Objective-C's approach?
Objective-C often relied on checking return codes or using special NS error pointer parameters to signal if something went wrong. It could be a bit clunky and easy to forget to check for errors. Swift introduced structured error handling with do, try, and catch blocks. It's a much clearer, more explicit way to write code that might fail, handle different kinds of errors gracefully, and ensure that errors don't just get ignored.
Swift also seems to embrace more modern programming styles like functional programming features.
Yes, definitely. While Objective-C is primarily object-oriented, Swift was designed as a multi-paradigm language. It has excellent first-class support for functional programming concepts. Things like map, filter, reduce, or build right in. These let developers write very concise and powerful code for working with collections of data, often leading to shorter, more readable, and less error-prone logic.
But Apple couldn't just flip a switch overnight. A lot of existing iOS code was Objective-C, so interoperability was key.
Absolutely critical. Apple knew developers had huge existing code bases in Objective-C, so Swift was designed from the start to work seamlessly alongside Objective-C within the same project. You can call Objective-C code from Swift and Swift code from Objective-C using a bridging header. This allowed teams to adopt Swift gradually, writing new features in Swift while still maintaining their older Objective-C code. That smooth transition was vital.
Okay, finally, performance and tooling. Is Swift actually faster?
In many cases, yes. Objective-C relies heavily on message passing at runtime. When you call a method, the system has to dynamically figure out which piece of code to execute. This offers flexibility, but has a small performance cost. Swift can often resolve method calls at compile time. It compiles down to highly optimized machine code using the modern LLVM compiler infrastructure. This generally results in faster execution for CPU-intensive tasks compared to Objective-C.
And the tools around the language.
Swift benefits from being newer and open source. It has a modern built-in package manager, Swift Package Manager SPM, for handling dependencies, a vibrant community, and rapid evolution. Objective-C is incredibly mature and stable, but its tooling feels a bit older compared to Swift's ecosystem.
So the shift was really about safety, speed, and bringing iOS development into a more modern era.
Exactly, setting the foundation for the future. Hashtag tag outro.
Wow, okay, so this deep dive really took us across, almost 20 years of iOS architecture, from that very first, pretty basic iPhone OS 1, all the way to this potentially huge leap with iOS 26, focusing on on-device AI and this liquid glass idea. We saw how things like the App Store, iCloud, the UI redesign, privacy features like ATT, how they all fundamentally reshaped the platform over time.
And we really dissected that core difference between iOS and Android, didn't we?
Yeah.
Apple's entire approach is built on that end-to-end control. Hardware, software, distribution via the App Store. That's the bedrock for its reputation, the optimization, the consistent performance, sticking to the HIG, the security focus, the long update lifespan.
Right, while Android trades that consistency for openness, customization, and just massive market reach because of all the different hardware options.
Exactly, two fundamentally different philosophies.
We also got right under the hood looking at those life cycles, how Apple enforces discipline on apps to manage resources and battery.
Yeah, the application and UI view controller lifecycles are key to making the whole system work smoothly.
And we tracked that necessary evolution from Objective-C, with its manual memory challenges, to Swift, a language designed for safety, speed, and modern development, using things like ARC and optionals to prevent common bugs.
Yeah, the move to Swift was about future-proofing the platform, really, making development safer and more efficient. The architecture consistently shows Apple leveraging control as both its main strength and its defining constraint.
Right. That control delivers the performance and security users expect, but it means developers have to play strictly by Apple's rules, the life cycles, the HIG, the App Store reviews.
It's a disciplined ecosystem.
Which leaves us with a final provocative thought for you to chew on. Given how essential those standard UIKit components, like UIDable with its cell reuse and the strict enforcement of the human interface guidelines are, how much does Apple's deep architectural control really dictate the final user experience? If consistency and optimization are the absolute top priorities, does that inherently limit certain kinds of functional or even aesthetic creativity that the more fragmented, maybe messier Android world allows, despite its own drawbacks?
That's the tension, isn't it? Control versus freedom, consistency versus diversity. It's the fundamental architectural trade-off between the two dominant mobile platforms.
Something to think about.
We'll leave you with that.
Thanks for diving deep with us today.
See you next time.